So, welcome back. Okay. So, we were having a go at capacitance and capacitors, that is condensers, which are the energy storage devices. And we studied in the last lecture, in the previous lecture, the parallel plate capacitor. And now we are going to have a study of the effect of dielectric on the capacitor. Okay. So, a schematic diagram that I have drawn here for the capacitor. There are two parallel plates. On one, I have the charge plus Q and minus Q, sigma, which is Q upon A, and minus sigma, which is equal to minus Q upon A. These are the surface charge densities. And so we have an associated electric field, which is having parallel lines, equidistant, etc., from one surface to the other surface. And right now, the capacitance of the system is C0, C0. Okay. Now what we do is, we enter a dielectric in the space between the two plates. A dielectric which will have a dielectric constant K that is entered fully into the system. So what happens? Before that, when the vacuum is in between, then E naught is equal to sigma upon epsilon naught. This is the magnitude of the electric field. And the potential difference V naught is equal to E naught into D. So C naught, the corresponding capacitance is equal to 2 divided by V naught, because Q is proportional to V. So this becomes equal to epsilon naught A over D. This is the capacitance when there is vacuum between the two plates. Okay. Now when filled with the dielectric fully, so what is going to happen? Let's see. What will happen to the charges on the plates? The charges on the plates will be undisturbed. Okay. They will not be disturbed. So what happens? That, as I told you, that when this is like this, then there is a polarization. And the effect of the polarization is that the sigma value is reduced. And so it's reduced the electric field. And when the electric field is reduced, then the potential difference will also be reduced. I repeat. When this settles, the polarization is there. So there is an electric field due to polarization which goes in this direction, which reduces the value of E, and the charge density at two plates, it reduces to sigma 1 is sigma P and minus times sigma 1 is sigma P. So that the corresponding electric field becomes equal to sigma 1 is sigma P upon epsilon naught. The separation is the same and the area is the same. Okay. Now, the field is reduced. The new field is sigma 1 sigma naught upon epsilon naught. And the new potential difference, which was equal to V naught, now it becomes equal to E multiplied by the D. Because E is equal to dV minus dVdr. Using that, I will write it that it is equal to sigma minus sigma naught over epsilon naught multiplied by D. Okay. So this is about the potential. Now, if our dielectric is linear, okay, if we have a linear dielectric, then this sigma P, the polarization, due to the polarization, is proportional to E naught, the field that exists otherwise. R, this is proportional to sigma. So I can write that sigma minus sigma p, the new charge density that is there, is proportional to the sigma itself. Or I can write sigma minus sigma naught, sigma minus sigma p is equal to sigma upon kappa k. Okay. Also we use capital K or kappa. The Greek term is this. Now this quantity is less than this quantity. Okay. So the K has to be, because it has reduced, so K has to be greater than 1. Has to be greater. And K is called the dielectric constant. Okay. K is the dielectric constant. K is the dielectric constant. So I get this relation. Okay. Therefore I can write now that the new voltage which is developed over here, there is sigma d upon epsilon naught into K, and sigma is equal to Q upon A. So I can write this Q d upon A epsilon naught K, okay, or epsilon naught K A. So from there I can write the new capacitance, which is Q upon V. Okay, value of V is there, so I can write this. V is there, and Q will cancel out, and I'll get this relation. Epsilon naught Ka upon D. Epsilon naught Ka upon D, where epsilon naught K is the permittivity of the new medium, permittivity of the dielectric. So I can write that permittivity of the dielectric as epsilon, and therefore I can write K as equal to epsilon divided by epsilon naught. So this K is a dimensionless quantity, just like what I introduced to you before, and I called it epsilon R. The relative permittivity, okay, and the dielectric constant are one and the same thing, defined in different ways. Okay, so next what we are going to do is we are going to tell you, I am going to tell you, we are going to learn about what is known as the displacement, electric displacement vector. So in continuation thereof I am going to deal with the electric displacement, capital T. This is a new vector associated with the electric field, and I'll just take you to the value of K, which we defined earlier as C upon C naught, where C is the capacitance with the dielectric, and C naught is the capacitance with that one. Okay. Now we are going to establish an explicit relation between sigma p, the polarization density, charge density, and capital P, the polarization, where polarization is defined as chi E into E, where chi is the susceptibility, okay, of vacuum. Anyway, now we are going to define sigma as a dot product P dot n cap, vector P dot n cap, without proof, of course. So we are not in a position to give you the proof, and just see that sigma P is because of the polarization, and n cap is the unit vector along the outward normal to the surface, outward normal to the surface, any surface for that matter. So this relation is true for any shape, any size of the dielectric that is inserted inside the capacitor. Okay. So we can write that E dot n cap. This I can write as sigma minus sigma p divided by epsilon naught, and this is given as sigma p is given as p dot n cap. Or if I just take this vector on this side and multiply it by epsilon naught, so I get epsilon naught E plus P dot n cap is equal to sigma. Okay. Now this quantity, the relation that we obtain over here, this quantity epsilon naught E plus P is equal to D. We call it electric displacement. And of course the P, the E, the D, their cap vectors are equal within unit vectors, all parallel to each other. So I can write the magnitude of D to magnitude of E, which is equal to D upon E. I can write it as sigma epsilon naught divided by sigma minus sigma P. And this turns out to be equal to epsilon naught into K, which gives the value of the displacement vector, okay, electric displacement vector is epsilon naught K into E, okay, and P will be equal to, therefore P will be given as D minus epsilon naught E, okay, P will be given as D minus epsilon naught E, right? So I take epsilon naught out and substitute the value of D over here, okay, epsilon naught K into E, epsilon naught K into E, and I will get this relation that P is equal to epsilon naught K minus 1. K, I told you, is always larger than 1, okay, therefore this quantity will be a positive quantity, epsilon naught K minus 1 into E, and therefore I can write, taking into consideration all things, that chi E, the susceptibility, is equal to epsilon naught K minus 1. Okay, so after this I am going to take up the beautiful concept of having capacitors in series and parallel. So now beautiful thing, very simple, combination of capacitors, purely series type, purely parallel, and mixed. Okay. We'll talk about these things. This is very simple to talk about. The key formula always is Q is equal to CV. Okay. Now I have two capacitors, C1 and C2, with potential difference here V1 and V2, and I have shown it here as a copper wire kind of a thing, but I will rather combine them directly like this. Okay, I gave it just to you an idea, because when the plates are there, then this is a connecting metallic thing. Okay, always here also and here also the metal is there. Okay, and from here to this whole body of the plate, everywhere the potential is the same. From everywhere over here, in what it makes an H on all points in this H kind of a structure is also the potential is the same. The potential is different here. Now the combination of two capacitors can be considered as a single capacitor with, now what will happen? When these capacitors are combined, then the charge on this plate, plus Q, minus Q, and then plus Q, minus Q, and if there are a large number of them, plus Q, minus Q, plus Q, minus Q, like that. And here also the charge is plus Q and minus Q. So the charge will be the same as I have shown over here, Q, Q, Q. plus minus like that. Okay. I can write now this equation. This is the key equation. Okay. V1 will be equal to Q upon C1, V2 will be Q upon C2, V will be equal to Q upon C, and V will be equal to V1 plus V2. So V will be equal to Q upon C1 plus Q upon C2, which is equal to Q upon C, and you can see that Q will cancel, and I will get an equation of kind 1 upon C is equal to 1 upon C1 plus 1 upon C2. Okay, 1 upon C is equal to 1 upon C1 plus 1 upon C2. This is the beautiful equation that we get. And now if I take the LCM of C1, C2, I will get C1, C2 over here, and then I multiply these two, then I will get C2 plus C1. Okay, which means if I reverse C, I will get the value of C as C1, C2 upon C1 plus A2, which I can say is product upon the sum for the couple of capacitors in series. Now look here, look at this equation. So 1 upon C is equal to 1 upon C1 plus something. So that means 1 upon C will be greater than 1 upon C1. Okay. So if I multiply both sides by C into C1, I'll get here C1, and here I'll get C. So C1 is greater than C, and similarly C2 is also greater than C. That means the net capacitance which we obtain, the equivalent capacitance, that C will be equal to, okay, that C will be less than C1, less than C2, less than C3, etc., and less than even the smallest value of C that is there in the combination. When I take general combination, okay. In general, let us have n capacitors. So I'll write the equation like this, okay, and then we solve it mathematically and obtain the value of C. The value of C1, C2, Cn are different, then of course the fractions have to be added and then reverse, and we get the value of C. Okay, now there is a case. I suppose this C1, this C2, the Cn, they are all equal, say equal to C star. Okay, then what will happen? 1 upon C will become 1 upon C star plus 1 upon C star plus 1 upon C star. How many times? N times. So this will become n upon C star. So the value of 1 upon C is equal to n upon C star, which gives reverse the value C will be equal to C star upon n, and n is greater than, here, look here, n is greater than 1, okay, therefore the value will get reduced drastically. That means if I have 10 capacitors, each of value 10 microfarads, and I want to have a capacitor of rating 1 microfarad. What I do? I put all of them in series, the 10 of them, and obtain a capacitor like that. The case of capacitors have just taken the analog in the case of springs. Okay, I apply the force when the springs are extended, then this spring is extending with the spring constant K1, the extension is X1, and K2, the extension is X2. The force here is F here and F here, and the same even if you take n of them, then, and the equivalent spring is X is equal to X1 plus X2. Of course the force is the same, so I obtain, after a little bit of exercise, I again get 1 upon K is equal to 1 upon K1 plus 1 upon K2, and the K value becomes equal to the product upon sum. So we arrive at that, and I tell you that when resistors are combined in parallel, then also a similar kind of mathematics will be there, which you can do in a very, very short while. Okay. So next, I take up the capacitors in parallel. So the next item is the parallel combination, and I'm combining first of all two capacitors C1 and C2 parallel to each other. Okay, this is indicative of parallel. So they are like this: C1 and C2, Q1 and Q2, two charges, and the equivalent. I have this charge Q over here. Okay, so the charge Q will be equal to Q1 plus Q2. Very simple. The key thing over here is that the potential difference across this and this will be the same as that across the combination. Okay. So I can write very simple: Q is equal to Q1 plus Q2, and from Q is equal to CV I can write CV is equal to C1V plus C2V, which will give V, and C is equal to C1 plus C2. Very simple. In general, the charge Q will be equal to Q1 plus Q2 plus Qn. V will remain the same, so I can write Q is equal to CV, Q1 is equal to C1V, Q2 equals C2V, Q1 is equal to CnV, and V cancel. So I'll get C is equal to C1 plus C2 plus Cn. So this is equal to, this is given as the sum of these capacitors. And if C1, C2, like in the last case, Cn is equal to C star, then C will be equal to Nc star. And to draw the parallel, I have shown to you the case of the springs, where the two springs are combined in parallel, give rise to a single spring, equivalent spring. The key thing here is that the x will be the same, and of course the f will be divided, f1, f2, f3, f4 like that. So f will be equal to f1 plus f2, so I can write like this, gets like this, and in case I have a k star, so it will turn out to be like this. Okay. So now the third thing is, if I have capacitors, a series combination of two capacitors, okay, then we have some capacitors in parallel, some capacitors in parallel, okay, and you want as to what will be the total capacitance between the points A and B. So how we proceed? First of all, we say that the sum of these two capacitances, then 1 upon this plus 1 upon this plus 1 upon this will be equivalent. So there are many things in the mixed combination that I will take up as next lecture will be about the problems regarding the combination of capacitors. Okay, and we'll do it fast enough with your help, provided you understand the series and the parallel combinations like this, and similar things we'll do again. Like here I've done the parallel case of the springs. Why the springs are giving the same kind of result? Because springs are also storage devices, okay, and like capacitors, and of course any storage device is also a dispensing device from which we can take energy out. So both are the energy storage devices. After I finish that, I'll tell you how capacitors carry energy and how an electric field anywhere in space, it also has an associated energy with it, like also the magnetic field has got an energy with it, associated with it. So I'll talk those things in detail in the next couple of lectures. Thank you very much for being with me.